Good morning, student. Let's start today's class. Today we will discuss about single stage common emitter transistor amplifier with voltage divider bias. Okay. Now on we will see that how the transistor biasing used for the amplifier. Okay. First of all, this is a single stage. Okay. In previously I told you that the amplifier circuit have a multi-stage, or in generally we use multi-stage amplifier. Okay, but here we and multi-stage means the combination of single stages. Okay, and the single stage means here we discuss about the single stage. Okay, then the and C means common emitter configuration. Okay, configuration is common emitter, and the biasing is voltage divider biasing. Okay, the both of these concept, common emitter configuration and voltage divider biasing, is discussed previously. Okay, now in single stage means, what do you mean by single stage? Single stage means that only single stage amplifier which consists of only one transistor with some assisting components with proper biasing system. This is called single stage. Okay, now here you see, this is the circuit diagram of single stage common emitter configuration voltage divider biasing amplifier circuit. Okay, this is our input. Okay, this is our input, and this is our output. The input is base emitter is input, and output is collector emitter. So because of the emitter is common here. Okay, then now let's see biasing circuit. Okay, the resistance R1, R2, Re from the biasing and stabilization circuit. The biasing circuit must establish a proper operating point, otherwise a part of the negative half cycle of the signal may be caught up in the output. Let it be. Okay, now first of all we saw that we see that input capacitor. That means there is a capacitor in our input circuit. Okay, and an electrolytic capacitor, okay, Ce in, okay, nearly equal to 10 microfarad, okay, is used to couple the signal to the base of the transistor. Okay, that means the which signal we applied to the base of the transistor, this capacitor is useful for coupling of that given signal to the base of the transistor. Okay, then if it is not used, the signal source resistance, okay, the signal source resistance will come across R2. Okay, if we didn't use C in, then the which signal source we used, that signal source have some resistance. Okay, that resistance is mixed with the R2. Okay, since there is a parallel, since the parallel connection established, so to avoid that, okay, we use C in. Okay, thus the capacitance C in allow only AC signal to flow, but isolate the signal source from R2. Okay, that means C in. Okay, C in also filter the input signal, or only pass the AC signal through it, and the second thing it does is that it isolate the resistance of source from the R2. Okay, so we use input signal for that. Okay, now input capacitor for that. Okay, now the second one is emitter bypass capacitor. Okay, that C why we use Re. Okay, but why we use C? Okay, in if you remember the uh, base divider, sorry, the voltage divider configuration, this much is there. Okay, 1 minute. This much circuit is there. Okay, there is no C in, no CC, no CE. Okay, but whenever we use that voltage or biasing method in practical use, we use some supporting components. These are the supporting components. Okay, so now why use common emitter bypass capacitor? This is called emitter bypass capacitor CE. Okay, an emitter bypass capacitor CE, which is nearly equal to 100 microfarad, is used in parallel with RE to provide a low resistance path to the amplifier AC signal. Okay, if it is not used, then amplified AC signal flowing through RE will cause a voltage drop across it, therefore thereby reducing the output voltage. Okay, so if this common this emitter bypass capacitor is used with RC, okay, to give a low resistance path to the emitter current. Okay, because here RE is have some resistance, but in capacitor path there is low resistance path. Okay, so whenever and if we it provide low resistance path, okay, to the amplified AC signal. Okay, amplified AC signal, IE is a amplified AC signal output. We can take the, sorry the IE is amplified signal, and if we didn't use it, okay, this C we didn't use here. Okay, what happened, the amplified AC signal flow through RE, okay, will cause a voltage drop. Here a voltage drop happened if we don't use AC the emitter bypass signal. Here uh, here became here the path became high resistive, and so whenever the I is flowing through it uh, uh, flowing through it, then um, then what happened, then a voltage drop is there. Okay, happened is there. Okay, now the signal flow through RE cause a voltage drop across it, thereby reducing the output voltage. Okay, so that the output voltage will be reduced. Okay, you know mm, if IE is reduced, then IC is also reduced. Okay, so since I IE we know I equal to IB plus IC. Okay, if I is decreased, let's say I is negligible, IB is negligible, IE also IC also decrease. This is IC is our output IE. Okay, so so we should use a emitter bypass capacitor CE. Okay, since this is called bypass, so it bypass high uh, amplified current. Okay, emitter current. Okay, now next thing is coupling capacitor CC. Okay, the coupling capacitor Cc, okay, which is nearly equal to 10 microfarad, coupled one stage of amplifier uh, to the next stage. Okay, if it is not used, the bias condition of the next stage will be dissatisfied drastically changed due to the shunting effect of RC. Okay, this is because RC is come in the parallel with the upper resistor R1 of the biasing of the network stage. Similarly, similar thing in the C in C in, or the purpose of C in is similar to the purpose of CC. Okay, so in the C in case, it isolate the R2, okay, from the source resistance. Here CC isolate the R1, okay, next stage of R1, that means R1 of next stage. Okay, if there is a next stage, okay, here R1, here R2, and here R1 and here R2. Okay, then also here transistor. Okay, so it connect from this, okay, this to base. Okay, so this CC separate this is R1, okay, of next stage. So RC and R1 is parallel. if there is no Cc. So to avoid this, we use Cc to isolate the R1 of next stage from the Rc. Okay. Now let's see. Now let's see the voltage, the various circuit current. Okay. Now let's see various circuit current is useful to measure the various current in the complete amplifier circuit. These are shown in the figure uh, 13 point 13.3. Okay. So you see here the current is what? IB is one current, IC is one current, okay. IE also one current, I1, okay. IE, small IE is current, small IC1 is current, okay. Small IC2 is one current, okay. Let's see let's see this current, okay. Now first base current, okay. When no signal is applied in the base circuit, DC base current IB flows due to the biasing circuit, okay. In previously in voltage divider of biasing, we have already seen that whenever there is no signal applied to the transistor, there is at the time there also be a base current, okay, due to the biasing of the circuit, okay. Now when AC signal is applied, AC base current IB is flowing, therefore will be the application of the signal total base current, okay. This IB, total base current, is called IB. This is whenever there is no signal, this IB current is flowing, and when there is a signal applied, then this IB current is flowing, okay. So total base current is capital IB and plus small IB, okay. Now collector current, okay. When there is no signal is applied, a DC collector current IC flowing due to the biasing circuit, okay. When AC signal is applied, AC collector current IC is also this capital, you remember this capital is due to the DC current. This is DC current, and this small IB is AC current, okay. Small I means AC, the capital I means DC, okay. Here also this I also capital IC, this is due to the DC current due to the biasing, and small IC due to the applied signal, okay. Now we know that capital IC equal to beta into IB, which is zero signal collector current, okay. Now IC, small IC equal to also beta into IB, collector current due to signal, okay. Then emitter current, okay. Now when no signal is applied, a DC emitter current IE is equal to similar things here also happened, okay. So total IE current equal to DC IE plus DC, no, sorry, AC IC. This DC IE is due to or this DC IE is when there is no signal applied, and this is due to the biasing of the circuit, and this I, small IE, is due to AC signal applied to the circuit, okay. It is useful to keep in mind that IE, this is, you know, IE equal to IB plus IC. Similar things, IE, small IE also small IB plus small IC, okay. Now base current is usually very small, therefore as a reasonable expansion IE is nearly equal to IC, okay. Now phase reversal. What is phase reversal? Okay, in common emitter connection, when the input signal voltage increases in the positive sense, okay, the output voltage increase in the negative direction, and vice versa, okay. In other word, there is a phase difference of 180 degree between the input and output voltage in common emitter connection, okay. This is called phase reversal, okay. In the phase reversal, okay, whenever the input voltage is increased positive, in positive sense, that means the input voltage is increased in this sense, okay, then the output get reverse 180 degree phase reverse, we get like this output, okay. So this is the 180 degree phase shift, okay. And this phase shift is called phase reversal. Okay, the phase difference of 180 degree between the signal voltage and the output signal is in a common emitter amplifier is called phase reversal. Okay, in common emitter, this phase reversal will be happened. Okay, uh, in generally. Okay, now consider a common emitter amplifier circuit shown in 13.4. This 13 point, this this is consider this this amplifier. Okay, now the signal is fed to the input terminal, that is between base and emitter, and output is taken from the collector emitter end of supply. The total instantaneous voltage, output voltage VCE, given VCC minus IC/RC. Okay, this instantaneous output voltage, this is VCE, V this this voltage VCE equal to this VCC minus the voltage drop here IC RC. Okay, so then here you see, whenever we feed this the this common emitter biasing circuit, we get 180 degree phase shift output. Okay, so remember, in common emitter amplifier, okay, the 180 degree phase shift or phase reversal is there. Okay, now when the signal voltage increase in the positive half cycle, the base current also increase. Okay, the that means whenever the signal voltage increase in positive half cycle, this positive half cycle, the base current also increased, this base current is also increased. The result is that the the collector current, and hence the voltage drop in IC increase. Okay, uh, since IB is increasing, okay, so IC also increase. Okay, so that ICRC, the voltage drop here also increase. Okay, as VCC is constant, since VCC applied constant voltage. Okay, this then we, therefore output voltage VCE, this VCE, okay, this voltage decreases. Okay, since we know VCC minus IC RC is equal to VCE, since VCC is constant, and whenever ICRC is increased, okay, whenever ICIC is increased, then VCC also always decrease. Okay, due to the minus sign. Okay, now in other word, as a signal voltage is increased, as the signal voltage is increased in the positive half cycle, the output voltage is increased in the negative sense, that is the output is 180 degree out of phase with the input. If it follow therefore that in the common amplifier emitter amplifier, the positive half cycle of the signal appears as amplified negative half cycle in the output of the output, and vice versa. Okay, and you see what is the then the graphical decomposition. Okay, what is graphical the effect of a phase reversal in common emitter connection can be shown graphically with the help of the output characteristic and load line. Okay, this is the load line AB here in figure 1.13 point, this figure. Okay, AB is a load line. Okay, this AB is a load line. The base current influenced between fluctuates between say plus 5 minus 0.5 microampere with 10 microampere as a zero. Okay, this is 5 microampere, 10 microampere, and 15 microampere. Okay, so the base current here fluctuate like this. Okay, now from the figure it is clear that when the base current is maximum in the positive direction, BC became maximum in the negative direction. Okay, point G, this G. Okay, that means whenever BCE is minimum, okay, you see it is clear that when the base current is maximum, okay, the base current, this is the 15 microampere, this is base current maximum, so Vc is minimum. Okay, Vc is became maximum in the negative direction. Vc is maximum in the negative direction. That means this Ib is max here, okay, and Vc is in the negative direction, okay, maximum. Okay, now this G point, okay, you remember this G point. Okay, now on the other hand, when base current is maximum in the negative direction, Vc is maximum in the positive direction in H point. Okay, whenever the Ib current, okay, this Ib current is minimum, okay, then the Vc current is maximum in the positive direction. Okay, this is positive direction, this is negative direction. Okay, you see, this is the Vce, and this is the Ic, and this is the Ib. Okay, thus in an input and output voltage are the phase opposition, or equivalently the transistor is said to be purpose a 180 phase shift reversal of the voltage with respect to the signal voltage. Okay, now this is all about your single stage common emitter transistor amplifier with voltage divider biasing. Okay, thank you.